Hey y'all, so I wanted to make a video looking at treating multiple objects as a system, right? And we did this in the mini lesson in my class, but I know that it was rushed for some of you, and some of you didn't ask as many questions as maybe you would have liked, and some of you just would like to see it again. And so I'm going to create this video is for you in the hopes that it'll be helpful in thinking about objects as a system, all right? Now, what we have is we have a cart that's on top of a frictionless table. The cart has a mass of 3 kilograms. It's connected to a string which goes over a pulley. The pulley is then connected to another mass which is hanging off of the side, and that mass has a mass of 1 kilogram. All right? Now what we want to do here is we want to be able to solve for all of the forces. We want to be able to solve for the acceleration. We want to just be able to find out what we can find out. All right? Now, what we learned first is that we should always start with a free body diagram. So if I look at the cart, okay, I'm going to label this as the cart just so I remember later that that's what this free body diagram is. Of course, we've got gravity pulling down. That's the only non-contact force that we've really talked about up to this point. Everything else should be things that are touching the cart. So what's touching the cart? Well, the table is touching the cart. The table is beneath the cart, so the table must be pushing in the normal perpendicular direction. So the table is going to push up. So I've got the normal force there of the table, right? And then I have the string, which is also touching the cart. Now, normally we don't refer to the string as having a normal force. Okay, the string has what we call tension, and if you've heard that word tension before, it usually has something to do with a string or cable that's tight, and therefore it's exerting a force on the objects on either end. And so that's what tension is here. All right? Now, if you think about it, there's nothing else touching the cart. A lot of students have the habit of trying to say, well, the mass is pulling the cart. No, the mass is not pulling the cart. The mass is pulling the string, and then the string is pulling the cart. So the thing actually pulling the cart is the string. The mass doesn't interact with the cart at all. All right? So there's my 3 forces. And many of you recognize that vertically, the cart is not accelerating, right? All of the acceleration, all of the motion is horizontal. And we learned that the vertical and horizontal pieces are independent of each other. They don't affect each other. So that's going to be really important later. But I am, for the moment, going to mark those 2 as equal because I know that those vertical forces are equal there. All right? Now I'm going to move over to the mass that's hanging off at the end. I'm going to do a free body diagram for that lovely guy. So he's got the force of gravity pulling down. And we've got the string, which is also touching it, right? The string is going to pull up on that mass. Now, you may say, well, is it really pulling up, Mr. Bowder? Is it really? Well, think about this. If you were to let the mass go, it would fall, right? What would happen if you cut the string? Would it fall at the same speed, at the same acceleration, or would it fall faster if you cut the string? Most of you are going to recognize that if you cut the string, it's going to fall faster than if it was still connected to the string, right? Because the string is connected to this mass, which is going to end up slowing it down. And so, yes, the tension does pull up on that mass. And so we've got the tension that is up. Now, you may or may not recognize this at this point, but the force of gravity must be larger than the tension. Don't get in the habit of just saying, oh, those are the 2 forces, they're balanced, it's equal. No, 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 no. It's definitely not equal because what happens? The mass accelerates downwards. If the acceleration is downwards, then the combination, the net force, needs to be downwards. And so therefore, the force of gravity must be larger than the tension force. All right? So now I've got my 2 free body diagrams. Now what we learned in the first example is that we can do Newton's second law for each of these objects. All right? Newton's second law is sum of the forces equals ma. And remember, sum of the forces really just means the combination of the forces. And so there's a couple of different ways to look at this. We really do need to add all the forces together. In AP Physics, you'll actually learn that we would write 2 equations here, right? One of those equations would be for the vertical forces, and one of those equations would be for the horizontal forces, all right? In this situation, that's really not that necessary because my vertical forces cancel out, right? So technically, I should be able to take the normal force of the table plus the tension, and then minus the force of gravity, and those should all add together to give me, sorry, not zero, MA. Now, in that process, recognize that the normal force and the force of gravity are equal, right? They're balanced, which means that these two forces are going to end up canceling each other out anyway, right? And so I end up getting that the only horizontal force is causing the horizontal acceleration. And so essentially we have tension equals mass times acceleration. Now, if I wrote a separate equation for the vertical forces, then I'd have this minus this equals 0 because vertically it's not accelerating. And I could do that, but right now that's not really important. Right now I'm recognizing that, oh dang, I've got tension and acceleration. I have two different variables there, all right? Which means I can't actually solve for either of them at this point. So let's walk over to the mass. Well, the mass only had two forces, so maybe that's going to be simpler, right? So again, we'll go sum of the forces equals MA. We've got the tension, which is up. We've got the force of gravity, which is down, so tension minus the force of gravity, which is then equal to mass times acceleration. Okay? Now, I can actually solve for the force of gravity, right? Because it told me that the mass is 1 kilogram, and I know that the force of gravity is always equal to mg. And so I can solve for the force of gravity by taking the mass of 1 and multiplying it by g, which is 9.8, and so I get 9.8 for the force of gravity. So I would have tension minus 9.8 equals the mass, which is still 1, times the acceleration. Now, what you'll notice is that, again, I still have two variables. Now, one option here is if I have two variables and two equations. I learned in math class how to deal with that using substitution or elimination or graphing even, right? However, if you do that, you need to make sure that each of your variables actually represents the same thing, right? Here, tension is positive, right? Because it's pulling to the right. Here, tension is positive because it's pulling up. And so those two t's would both represent a positive number. That's good. That's good. We're good. However, the acceleration, notice that the acceleration of the cart is to the right. So this a would be positive. But this one is accelerating downwards, so that a would be negative. So those a's are actually not the same thing. Now, you can resolve that just by putting a negative in front if you want, right? And if you put a negative in front, that would then allow you to solve using substitution or elimination or whatever. All right? However, the point of this problem, the point of this video is to say, you know what? We really don't have to do that. We don't have to do that fancy math stuff. As much as I love Algebra 1, Algebra 1 was my favorite math class. As much as I love Algebra 1 and the cool things that we get to do there, there's some cool physics things that we can do that allow us to avoid using that higher level math stuff. Higher level math stuff, right? So what we can do is we can treat everything that is connected, everything that's moving together as a system. Kind of like we had a problem before where we had a sprinter that was starting at rest and they started sprinting, right? And as they started sprinting, they were speeding up and accelerating. We didn't look at the head and the arms and the body separately because they're all attached. They're all moving together, right? Even though the ground was technically only pushing on the feet, we didn't have to look at how the feet were connected to the legs and the legs connected to the knee and, you know, the song, all that stuff. We didn't have to worry about any of that, right? Just like when we do a car. What's the ground actually pushing on? Well, the ground's pushing on the tire. But we don't have to worry about how the tire is connected to the axle and the axle is connected to... We don't have to worry about any of that. We just treat the whole car as a single object. We treat a whole person as a single object because all those pieces are connected. They all move essentially together. Now, obviously, it's a little bit more complicated than that, especially for a human body where things are kind of moving at different paces. But in the big picture, we can make the general assumption that it's a single object that's moving together. And we've been fine with that up to this point. So what we're going to do is we're going to take all those objects that are connected, the cart, the string, and the mass hanging off the end, and we're going to pretend that that is one single object, which it really is, right? It's all connected. As this falls, that moves to the right. Everything moves together, right? It could just as well be a single sock that's bent over the edge of the table that's going to accelerate as it falls, right? I mean, it could be anything, all right? We're going to treat that as a single object, and we therefore call it a system, all right? So what I'm going to do over here is I'm going to write the work for the system. Now, I'm going to do Newton's second law again. Sum of the forces equals ma, the same thing that we did here. But in the system, we only need to worry about external forces. The internal forces, like the forces holding my arm to my body, are internal. They don't affect the outward motion of my object. Okay? So again, if I look at the forces, there are no new forces just because I'm looking at a system. I just look at those forces a little bit differently. Notice that these two cancel out. So those are going to cancel out. They're not going to be important. I've got tension here and tension there. Number one, tension is now inside my object, right? It's like the tendons and the ligaments that are holding my body together. That is all internal now. Now, even if you didn't treat it as internal, this tension is going to make the object pull that way. This tension is going to make the object pull this way. So those are actually equal and opposite. They're going to cancel each other out anyway, right? As long as it's internal, then they're not going to be important. So we said that these guys cancel out. These guys are internal. Therefore, the only force that I have left that is important in the acceleration of my object is the force of gravity on that mass. And I already know what that is. That's 9.8 newtons. And so I can actually, for the sum of the forces, this is just going to be the force of gravity on the mass. And that's the only force. It's greatly been simplified due to looking at the system instead of looking at individual objects, right? So the force of gravity is 9.8 newtons. The mass is the mass of the system. Because, yeah, this is the only object that the gravity is pulling on, causing it to accelerate, but it's causing my whole object to accelerate. And so I've got 3 plus 1. So my mass is 3 plus 1 there, and then acceleration, right? We add the 3 plus 1, so we have 9.8 equals 4a. Divide both sides by 4, and we get 2.45 meters per second squared equals the acceleration. Ta-da! How about that? We didn't have to use any fancy math, right? We just used that idea that we can treat those objects together as a system. All right? So hopefully that was helpful. Now, of course, from this point, you can use that acceleration and you can put it in to solve for the tension, right? You can put it in then to solve for the other forces. The force of gravity, we already could have found that, right? We could have gone equals mg. We could have found that. This one's equal to that, so we could find that one, right? We already know this one. So the only force that we have left is tension. Tension will be the same throughout the string. So if I can find one of those tensions, then I'll have the answer. So you can just plug it back in and you get the answer. Keep in mind that in this equation, acceleration is positive because accelerating to the right. In this equation, acceleration is downwards. And so if you put this 2.45 in there, you need to put a negative in because it is downwards and we haven't accounted for that negative yet. All right? Unless you put the negative in there before when I mentioned it. All right? So that's it. That's it. The whole idea is that we can treat objects that are connected as a single object, as a system. And very often that will simplify things because some of the forces will become internal. All right? So again, I hope that was helpful. I hope that gives you a little bit of direction on how to deal with systems. We'll see you next time.